Okay, so for my Zoom folks, I have shared my screen. And can I just see a show of hands to make sure that everyone can see my screen and hear me? Fantastic. Okay, super. So we got 3 things on the agenda for today. Georgia, got a question. Question? Before we get started?
No, I'm sorry.
Okay, no worries. Okay, I do have a question from another student that I'm going to address about arrays and methods. Before I do that, I just want to show you what is on the agenda for today.
It's kind of complicated.
So today's agenda is going to be JarFiles, garbage collection, how it's implemented, and enumeration types in Java. So those will be the 3 topics up for discussion today. Before we get to that, I had a good question about what happens when you pass arrays into methods and what you can change and what you cannot change in the array. So let me actually create a short program. Call it array.java. And actually we don't, so we'll do vi example. Okay, so we'll create a class example and we'll have a example. And what we'll do is create an array here. So we'll say int a equals 1, 2, 3, 4, 5. And then we will call a function and pass it that array. So we'll say array changer and we'll pass it a. And when we're done, we will print out the results. We'll say for int element of a system.out.println a sub. We don't know, we'll just print out the element. Actually, in this case, we probably want the index element. So I'm actually going to say for int I equals 0, I less than a dot length, plus plus.
So today is definitely an interactive lecture today. Have a whole bunch of
Did someone kill that?
queries that I'm going to have.
Is that me? Or someone else? I think that's someone else.
I think someone was playing a recording of you, sir.
Yep, I think you're right. Okay, got to kill that.
They were catching up on 465.
Okay, gotcha. Okay, so we got I, and we'll print out. So ace of I plus equals plus the ace of I is. Okay, and now we'll create void array changer. It takes an int array. First thing we're going to do is we're just going to change element 3 to be 10. That's all we're going to do. Okay, so public static public void main string args, and we're going to call new example. Okay, so the first thing, all I'm going to do is I'm going to show you that you can change the elements of an array inside of a method. Okay, so when this comes out, it should have 4, which is element index value 3, should be replaced with 10. Okay, so we will compile that. Run it. And you can see that element 3 changed to 10. So I can pass an array in, and you remember I said, okay, so it's passed by value semantics. And so how is it that I'm able to change the value of the array? And the answer is because I'm passing in a pointer to it. So I am so on my stack, for example, I have the stack, and it has A. And A is a pointer to this array, which has the elements 1, 2, 3, 4, and 5. And then I call change, or I think I called it array changer. And it gets passed a pointer to this array. So it's okay when I say x of 3 equals 10, it goes in and it changes that value to 10 because x points to the same element as A. Now let's say instead what I did was that down here I said x equals new int, say 5, and in fact I'll give it, can't say, yeah, x equals new int 5. And I go through and I initialize it. Okay, so I've assigned a new array to x. Okay, and I gave those values, I gave it the values basically 0, 10, 20, 30, 40, right? So now when I go back and I run this code, something, I have an error in here somewhere. So now it's still 1, 2, 3, 4, 5. So the thing is, when I assigned x, when I said x equals new int 5, I broke this connection. This connection no longer existed. X now pointed to this new array, which I set to 10, 0, 10, 20, 30, and 40. But A still pointed to this old array. So while I can change the contents of A in the subroutine, I cannot change the array to which A points in the subroutine. Okay, that's the difference. So, and you can do that, in fact, to any object. You can change the contents of any object in a subroutine, but you cannot change, you cannot make it the original, you cannot make the original A point to some other object in the subroutine. That can't happen. So hopefully that clarifies that particular question. See if, okay. So, good with that? Okay, so let's start with enumeration types as the first thing to talk about today. And for that, I'm going to go back to okay, so most of the time, you will employ enumerated constants in their most simple form, which is you will simply declare the type of constant, in this case day, you'll put curly braces and you'll give the enumerated constant. So it looks fairly much like C++. The difference is that actually each of these, so day is going to be a class. Java treats day as a class. It declares day as a class. It actually compiles it. Okay? And Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, they're a fixed set of constants, but they can actually be instances of this class. You're allowed, they don't have to just be integer constants, which is what they are in C++. In Java, you can make each of these constants be an object that has values associated with them, that allows you to execute methods on them. So a good example of that occurs in graphical interfaces, where you might have something like public enum font size. And you want to declare them as, say, small, but now you actually want to give them point sizes. So small should be of a point size of 10, medium should have a point size of 12, large should have a point size of 16, and extra large should have a point size of, say, 24. So in this case, you actually want to associate a number with each of those constants. And that's something you can't do in C++. And Java thought, well, this is something that could be helpful. In fact, it is helpful with graphical user interfaces because you end up with these kind of constants fairly frequently where they need to have additional stuff associated with them. Another good example in graphical user interfaces is colors. You'll have public enum color, and then you'll have something like red, and you have to give it RGB values. So it will be like 255, 00, because that's a pure red, whereas you might have green. Well, that's also an RGB, yellow. Can't remember what the exact values are, but there's a 0 there and some values for green and blue. I'll say 50 and 100 just for grins. Okay, so these would be what are called RGB, red, green, blue values, which are mixed to form a color. And the user would only use the constants red, yellow, green, blue, but actually each of them is carrying RGB values that indicate how to create that color. So the designers of Java said, essentially, wouldn't it be cool if these enumerated constants could actually be objects? And that's what they did. So one thing, the book makes it a point, and I will reemphasize that point, Generally, when you refer to an enumerated constant, you have to give the name of the class and say like day.Sunday, day.Monday. And that's to avoid ambiguity because two different enumeration types could have the same names for the constants. Of course, Java goes right down into its example on its page, and it doesn't use these. And you're saying, wait a minute, aren't you always supposed to have the name of the class in front of the constant? And the only reason they're not having to put it there is it's inside a switch statement, and they know the type of the variable. And that's the only reason. But in general, you have to include would have to say capital DAY dot Monday here. Okay. So here's an example involving planets. So they got the planets of the solar system, and they're giving the mass and the radius of each planet. So here they're creating 9 instances of the constants. And in Java, the constants have to come first. They're comma separated with a colon. And then after that, you can have instance variables that are associated with each of the instances. So each of these constants will have 2 values representing the mass and the radius. And you can see that they're declared as constants. So once they've been initialized down here in the constructor, so again, remember, planet is a class. And each of these, Mercury, Venus, Mars, is calling this particular constructor and initializing the mass and radius. And you can assign in the constructor, even though these are constants, you're allowed to initialize them in the constructor. Afterwards, you can't change them. And then they have methods associated. Each constant has methods associated with it that allows you to query for its mass and its radius. Just like when I created the font, I'd probably have a method called getPointSize. So I'd have a way of getting at the point size. For each color, I'd probably have getRed, getBlue, getGreen, so I could get the color values associated with it. And then they went way beyond what anything I would ever do. But they said, hey, just to show you how great our invention is, we can even associate additional methods with the constants that do calculations, in this case on surface gravity and surface weight, based on the mass and the radius. The chances that you would actually go this far are pretty minuscule. I've actually never had these types of methods that do calculations with my enumerated constants. But I work in the area of graphical user interfaces, and I have used the feature of enumerated constants to assign properties to my constants, and that's really handy. Okay. So at any rate, you can if you need to get access to the values of the enumerated constant, hint, on the homework assignment, you will have to get access to your enumerated constant. So you will have something, a for statement that looks like this in your homework assignment. The dot values returns an array of the constants in the order that they were declared. So in this case, you would get them in the order Mercury, Venus, Earth, Mars, Jupiter. And here they're printing out the, let's see, the planet name and the surface weight. Okay, so here's your introduction to printf. We'll get into printf in more detail next week. but you can see that you can print strings and floats. They look just like they do in C++. I'll make the point now, and I'll make it again next week. You don't use \n in your printf statements in Java. You use %n. And that is because in Microsoft Windows operating system, \n doesn't actually always give you what you would expect. I think it has to be translated into a return and a form feed. So you're supposed to use %n for new line characters in Java.
I have a question.
Okay, just a sec. I'll get you in 1 second, okay? You'll notice here, P is, what does P stand for? Because there is no, it can't stand for mass and it can't stand for radius because those were defined. It turns out that P will print out the value of the constant, Mercury, Venus, Earth, as a string. So when you just get that value, this P is actually going to print the enumerated constant, but it will print it out as Earth or Mercury. It won't print it out as 0, 1, 2. Okay, now I'll take that question. What was the question?
What determines the ordering of the values associated with the constants?
It is in the order they're declared. So they will be given to you in the order that you declare them.
I mean with mass and radius. So there's two values associated with each constant here.
Okay.
What determines the order that they're associated with?
Right here in the, see this constructor?
It's the order of the parameters in the constructor?
Yes.
Okay, thank
So
you.
since it says mass gets the first parameter and radius gets the second. So I will tell you that the first couple times I looked at this, these constants, I thought this is a mess. It's complicated. Why did they ever do this? This is like this, I don't know, 8th or 9th time I've taught enumerated constants. And this was the first time when I read through this and I thought, wow, this is obvious and simple and makes all the sense in the world. And I told my wife that I better be careful because I need to remember that the first time I looked at it, this looked really complicated. So if this doesn't seem intuitive to you, I will tell you that the first couple times I saw it, it did not seem intuitive to me either. Looking at this for like the 8th or 9th time, for the first time I looked at it and thought, wow, this just flows really nicely. So now I feel like I understand why the designers put this feature into the language, but it will take you some time probably to process it. Okay, and that's why there is a homework question on enumerated types. So other questions about enumerated types? Okay. The next thing we need to discuss is JarFiles, which is how you are going to be submitting your programs to us so that we can basically execute them. So Java does not compile down to machine code the way C and C++ do. So you don't get an executable. What you get are .class files, and they're not executable unless you run them through the Java virtual machine. But you would like to be able to simulate an executable, and the way we do that is with JarFiles. So it turns out that you can execute JarFiles on the command line, and I will show you how. But before we do that, we have to, so that's the punchline. The bottom line here is when we're done, you're going to be able to execute a Java program kind of like it's an executable, but maybe not. I guess it's still, you have to use the Java command, so no. But at least you can bundle it up and execute it like it's an executable. So jar stands for Java Archival File. And they were super creative when they designed JarFiles. They looked at the tar page, the man page for tar, and they shamelessly ripped it off. So if you know how to tar up files, you essentially are good to go with JarFiles. If you don't, well, you're going to learn how to do jar in this course, and then you'll know how to tar up stuff, because essentially they do the same thing. So a jar file is just a collection of any files that you want, but normally they consist of .class files. In this course, because we want to be able to look at your source code, we will also make you include source files, .java files. But when you distribute jar files to the public, typically they only contain .class files. They typically don't contain your source code. So jar files were designed as a way to transmit a project and have all the files in that jar ball, okay? So if you want to create a jar file, the command is jar. The flag C stands for create, just like in tar, and F stands for I'm going to give you the name of the file. So this is the name of the file, and the rest of the files are the ones that you want placed in the jar file. Okay, so let's just do that. Okay, I'm going to jar up one called example.jar, and I'm going to stick example.class into it. Okay, so now I can look at it using T will show me the contents of the file. F again says I'm specifying what the file is. So you can see the jar adds some additional information, which you don't have to worry about, and then it has example.class in it. Okay, if I wanted instead to associate everything with example, I could say example.star, and now it's got both the Java file and the .class file.
Dr. Van der Zanden?
Yes.
So I noticed that you, when you were creating that example.jar file, you didn't create a manifest file.
Right.
Is that just something you need to worry about, or does it just do it automatically? Because I actually had to, I just manually created mine. But
It does not do it automatically, so I'm going to get to that, okay? Because
okay.
if it's going to get to, just a sec, I want to check something. I don't think this should work. Yep. Whoops. Yes. Okay. So it says no main manifest attribute. So I haven't yet. All I've done so far is shown you how to create a jar file and add some files to it. I have not actually shown you how to make it executable. That will be the manifest, and I'll get to it. Okay.
Okay, gotcha.
So I can also tar up directories. So I could come out of play and I could say jar cf example.jar play. And now everything, if I do a jar tf example.jar, it includes the entire play directory, which is huge, obviously. So it started though, the point, it stored a directory called play. It didn't put all the files associated with play into the top level. It created a top level directory, just like tar would. Okay, and then it did it. So now I am going to remove example.jar, go back into play, where I still have, I think I still have an example.jar existing. Okay, so I want to extract the contents of that jar file. The way I can do it, first let's get rid of those two. All I have is okay, all I have is example.jar. If I say jar x for extract file, example.jar, now it extracted them. And just like you have a verbose in tar, you can say extract verbose, and then you'll see exactly what you're getting out of it. So here it says, okay, I created this meta/-imp, I created that, created example.class. So the V flag stands for verbose. It tells you when you're extracting what you're extracting. When you create it, it tells you what you're creating. Okay, so I've told you how to create a jar file. So that's when you create one for the homework. We want you to jar up both your .java and your .class files. And then we'll be able to extract them using the jar command. And the final thing is you want to be able to execute. We want to be able to execute it without having to extract all your files. And the way that we're going to do that is by giving the -jar option to it. But we also, in order to make it, quote, executable, we have to specify the entry point. That is the class that should be executed. The easy way to do that is with the E flag. So when I jar it up and create it, I can say C, E, F. And now the order is important because I said the E flag first. I have to give the entry point, which is example. That's the entry, that's the class. Then I give the file, which is example.jar. And then I'll actually give it the class. So the order that you specify the flags is then the order that you specify the parameters for those flags. If I had said instead CFE, I would have had to reverse example and example.jar. Okay, so when the E specifies an entry point. So now if I say Java jar example.jar, it executes. Okay, and if I look at the it still has the same, it looks the same, but now it knows how to get to the entry point. So that's the easy way. The way I suggest that you create executable jar files is to use the E flag when you create the jar file and specify the entry point, which is the class. So the entry point is the class that contains main. That's your entry point. But you can also do it with something called a manifest file. And it's important that you know about manifest files because that entry flag was not added until relatively recently. So it used to be that you had to provide a manifest file in order to specify the entry point. And by convention, it was called manifest.txt, although you could name it anything you wanted. But the important thing is it typically consisted of one line, which was the keyword main-class spelled exactly that way. And then the class name was your application entry point, the one that contained main. So the other way that you can do it is you can create a class. So I could have instead created manifest, let's do it here, bi manifest.txt, change it to example, and I have to have a new line. Okay, it's really important that there be a new line. Otherwise, things go wrong. So now when I created the tar file, I would say CM for manifest file F. So now I would indicate that this is the M, is the name of the manifest file. So I can name it anything I want, but I have to include the M flag, and then I would say example.jar, and then I would give the class. Okay, and again, I should be able to run it. It works. Look at the contents. Still looks the same because it's basically using the manifest file to create the entry point. Okay, there's some other stuff associated with manifest files that aren't particularly germane to this course. So I'm not going to go over them. All I will say is my recommendation is to use the E option to create it, but you are allowed to use manifest files. If you use manifest files, make absolutely certain that there's a new line in your file. Otherwise, it doesn't go well. Okay, so let's just go back here for a moment, go into that manifest file. I'm going to delete the new line. I'm going to go back, jar it up, and run it. And it's probably going to work and make a monkey out of me. It did. But the documentation, it did make a monkey out of me, but the documentation is pretty explicit that you're supposed to have a new line after main class. Okay, so I gave you some examples. So feel free to do them. When we get to packages, we will come back to JarFiles because there is stuff associated with the directory trees and the like that's important then. But for the time being, all you have to do is for each of the different problems in the homework assignment, so problem 5, you're writing a min, so you're going to jar up min.java and min.class and specify min as the entry point. For this problem 6, you're going to jar up salary.java and salary.class, and you're going to specify salary as the entry point. Okay. So that's what you'll be doing for 6 or problems 5 through 8. So questions about jar files?
I
Okay.
have a question.
Yep, go ahead.
So let's say I forgot to add my .class file when jarring up something. So how would I retroactively add a file to a jar file?
I would suggest that you just create it from scratch again, just like I was doing. It will overwrite it. I'll be honest, I'm not sure. I forget how you add new files to a jar file. I would just recreate it from scratch.
Okay.
Because it'll just overwrite it. So if like here, so I start out, I'll show you, I'll forget it. So I say entry point, let's see, create entry point file example.jar, and I'll just include example.java. Okay, so I forgot the .class file. I try to run it, and it can't find or load main class example. Okay, darn it. All I would do is just go back and, in this case, turn it to example.star, and now it's happy. So it just overwrote what was there before. That's my solution.
Okay. And I do have one other question in regards to the homework and manifest files. I don't think I actually put a new line at the end of any of my manifest files, but all the homework seemed to run fine when I ran it from the jar file. Is that okay? Or should I go back to
Yeah, as long as it does, if you get zeros for it, just tell the TA, hey, it worked for me. So the question was, I didn't have new line characters at the end of my manifest files, but they were working. You saw it just worked for me too. So my guess is they've recently changed it so that you no longer need, I mean, it was silly that you had to have a new line. So my guess is they changed it so that
Okay.
it's not required. So I wouldn't worry about it. If it was working for you, I'd assume it's going to work for the TAs.
Okay, thanks.
Okay, just my one caveat is test it on the Hydra machines. Again, if you may have a version of Java that's like, I think it's all the way up to 1.15 now. Okay, installed on your machine. So just make sure it runs on the Hydra machines because we only have 1.8 installed on our machines. And for those of you who wonder why we're running 1.8 rather than 1.15 is because virtually nothing of any significance was added in 1.9 through 1.15. Okay, I mean, nothing that you care about is in there. It is tiny fixes plus an experimental garbage collector. Okay, other questions? Okay, so we move on to kind of the meat of today, which is garbage collection, how it is done. So I think it's important that you know how garbage collection is done so that you understand what the strengths and weaknesses of it are and why sometimes it can appear to fail in the sense of not collecting stuff that you expect it to collect. So there are two main types of garbage collectors. There are reference counters and there is tracing collectors. Reference counters, many of you have probably heard of smart pointers in C++. They're kind of, I forget which version of the C++ standard they were introduced in, but essentially smart pointers in C++ are reference counted pointers and can be automatically deallocated without your intervention. So basically what is happening with reference counting is that every object allocated off the heap. So with reference counting, every object allocated off the heap, or every heap allocated object, has a 4-byte block that keeps track of the number of references or the number of pointers to that object. Okay, and when this reference count goes to 0, it's called a reference count. So when this reference count goes to 0, the object can be garbage collected. Okay, so why a 4-byte block when we could probably do it with 1 byte or 2 bytes at most? And the answer is because everything is word aligned. So you're not really saving anything by making it a 1 or 2 byte block because everything's word aligned anyhow on 4 bytes. So obviously one problem with reference counting is every object carries with it an overhead of 4 bytes. So actually let me quickly show you how it works. So here's a very simple example. I set string A equal to new string hello, and now A points to hello, so the reference count for hello is 1. Then I set string B equal to new string world, so now we have world also has a reference count of 1. And now I assign A to B, that is I assign the pointer to hello to B. And so now B's reference count goes to, hello's reference count goes to 2, and world's reference count goes to 0 because nothing, B used to point to world but no longer does. So after this assignment right here, you can garbage collect world. So pretty simple. Okay. So what are the advantages? So this, I mean, it cannot get any simpler than this. So that's the advantage of reference counting. It's very simple. The cost of garbage collection is distributed uniformly over a program's execution. So basically, anytime an object can be garbage collected, it is. So you don't, it's just, it slows down the execution of the program, but not in any noticeable way. Okay, disadvantages. So you have to add a reference counting statement before and after every program statement that performs a pointer assignment, because you have to increment one pointer that's getting the new assignment, and then the object that's losing the pointer has to be decremented by 1. So you basically increase the cost of a pointer assignment by 3 because 2 objects are affected by every pointer assignment. One increases the reference count, the other gets it decremented. So there's 3 operations, so that increases the cost. This one is huge. You can't garbage collect circular structures. So if you have A points to B, points to A, such as in a linked, doubly linked, or in a linked list, you're never garbage collecting this thing. So let's say from the outside you have head points to A. And now we have A, C goes to D, goes to E, and we make head point to C. So at this point, this structure right here is orphaned. But because A and B each have a reference count of 1, it can't be garbage collected. So reference counting flounders big time on these circular structures, meaning that if you have these kind of circular linked lists with reference counting, your memory is going to keep getting bigger and bigger and bigger. Okay, so that's one way that garbage collection can fail is reference counting can't garbage collect circular structures. And then I've already said every block has an extra 4 bytes. And now this last one isn't as obvious. So let me go back here. So let's say that I have class node, and I have person P. No, I have this person P, and I have some other stuff. And so I have a node N, and now I say person star no person pointer equals the address. So I don't want, make this clear, I do not want that there. This is not a pointer. Okay, so actually, better yet, this isn't quite what I want, so this is what I want. So what I have done is I've created a situation, and now I say node P equals, oops, yeah. I say N equals new node. So what I have is in pictures, N pointed to this node object, and it has a person, P in it. So it has a person object. And then I created this pointer PP, which points to person. And then I made node with this, so that's 1. This is 1. 2, this is 2. And statement 3, I made node point to a different node. So what happens if I now garbage collect? So it looks like N, it looks like node now has a reference count of 0, right? But there's a problem. If I garbage collect node, what happens to PP? It becomes a dangling pointer, right? So I have an issue with reference counting that I can assign pointers to objects that are nested within a memory object. So I can't just rely on the outer reference count because there may be things inside of it that are also pointed to. So this is point number 4 here. It assumes a strongly typed language because the compiler needs to do what to do with a pointer that references a field in the memory in the middle of a memory block. Okay, so what it needs to be able to do is actually say that when this pointer assignment happens, it acts, so when one occurred, the reference count was 1. When this thing executes, it needs to make the reference count for this block be 2. So when this happens, it needs to know that this pointer assignment is occurring from within this memory block that is node, and it actually increments node's reference count to 2. when I assign this new node to n, it decrements this reference count back down to 1, but it won't get garbage collected because it knows there's still a reference to it. So with reference counting, you need to know what is the layout of each object, because if a pointer is made to an interior object like was done here, you actually increment the reference count for the enclosing structure. Does that make sense? Okay. Here in the class, everyone's nodding. Does that make sense to you all on Zoom?
So the second line here actually increases n's reference count to 2.
Yeah. Yeah.
So when you create a new node, n's reference count is still 1.
So it's not actually n. So it is the object that n points to.
Okay, but the person thing has a count of 1 still.
Person does not have a reference count associated with it.
I guess I'm speaking poorly here. The thing that n was originally pointing to still has a reference count of 1.
Correct.
Whenever we assigned a new node.
Yes.
Okay, thank you.
That is correct. You're right. So the point is, person itself does not have the 4-byte code. It is the structure enclosing person, namely node, that has that 4-byte reference count. So you got to know which one to increment. So that makes reference counting more difficult than you might imagine. Okay. So turns out that this disadvantage is enormous. And so modern garbage collectors don't use reference counting. Now, smart pointers, they're just implementing a restricted form of garbage collection, so that's fine. But Java doesn't use it, Python doesn't use it. Any scripting language that uses a garbage collector pretty much uses a tracing collector, not a reference counter. So let's get into what tracing collectors do. Okay, so again, let's say we have n. Let's actually go back to this example right here. See if we can do it from here. See if I can do it with an annotation tool. Okay, so these 3 statements right here. Okay, you have, yep, okay. When the first statement, so we'll say 1, 2, 3. So when the first statement executes, we have A pointing to the string hello. Then when the second statement executes, B points to world. And then when the third statement executes, B is made to point to A. And this one goes away. So the way a tracing a collector works is the first thing you do is you walk through the heap, which in this case consists of hello and world, and you mark them all as useless or not visited. So we'll just say useless, useless. So you go through the heap, and for every element in the heap, the first step is to mark them all useless. Then you go through the stack. Okay, this is the stack. And for each pointer on the stack, you do a depth first search. So starting at A, you do a depth first search. You see hello, and now you mark it great as used. Useful. So we'll mark it. Let's make it let's go with true and false. So we'll say, we'll start with, so what we're going to do is start by saying everything is false. So meaning it's not used. F means not used, true means it's used. So we now go to A, we visit hello, and we say, ah, something references it, so we mark it as true. And hello doesn't point to anything, so the depth first search stops there. Then we go to B, because it's on the stack, and we see it goes to hello, but hello is already marked true, so as depth first searches want to do, we stop. And now there's no more pointers to follow on the stack, so step 2 is done, which is the mark step. Now we go to step 3, which is we again sweep through the heap, and any block that is marked F for false is removed or returned to the memory allocator. So at this point, world is returned to the memory allocator. Okay, so it's a 3-step process. Step 1, we mark everything as on the heap as false to indicate not being used. Step 2, we go to the stack. For every pointer on the stack, we do a depth first search of the pointer. So if hello, for example, was a object like a node, let's say instead of it being hello, that A was let's see. Okay, let's say that A, instead of being hello, A points to something that is got first or next and previous. In that case, we would have started with false, false, false. And when we followed A, we would mark this as true, but then we would descend into A and follow every pointer in A. So it's next, that becomes true. Come back, depth first search, go to previous, which is the next pointer in A, and mark it as true. So that's why it's a depth first search. Okay, so that's step 2, the mark phase. And then the third phase is the collect phase, where we go and we collect or garbage collect anything that has a false. Okay, and there we go, clear. Okay. So the tracing collector I just described is called mark and sweep. And it's just the 3-step process that I just told you. Step 1, walk through the heap, mark every block as useless. Step 2, for each pointer outside the heap, i.e. on the stack, do a depth first search, mark all blocks encountered as useful. Step 3, walk through the heap again, move every block still marked as useless to the free list. Okay, so advantages, less overhead because it's only called when free memory is exhausted. It's not keeping track of reference counts the way that reference counting was, and it doesn't need a 4-byte block at the beginning of each allocated object. Big advantage, it garbage collects circular structures. Okay, circular structures are going to be not found if they no longer have pointers to them. So they can be garbage collected. Disadvantages. They can cause long, annoying pauses when garbage collection occurs. The reason is they're typically not called until memory is exhausted. Well, in modern computers, it takes a lot to exhaust virtual memory. So when that happens, it takes a fairly long time to walk through the heap, mark everything useless, then do each of the next two steps. So you may not notice anything in a batch program. Like if you're running something that is doing numerical computations or simulation of a planet, you may not care. But if you're running a graphical user interface, and all of a sudden the graphical user interface freezes because you're doing garbage collection, that's bad. Okay, or you're running some stock trading algorithm and you're in the middle of executing a trade and all of a sudden it garbage collects for 5 minutes, and when it comes back, the trade is no longer a good one. Okay, so this was 20, 25 years ago, but this is what happened with GUIs with us. We were using Lisp and would be doing something in the interface, and all of a sudden it would garbage collect, and the joke was we'd go out for a cup of coffee because that's how long it would take before the user face would be useful again. Okay, so there are solutions which are to use incremental garbage collection that gets kicked in periodically before memory is exhausted. And that leads to some threads because you need to now have the garbage collection on one thread, the application in another. Increases book creeping. It goes from something that's fairly simple to more complicated. We won't worry about it. Just know that the simple mark and sweep algorithms can cause long, annoying pauses. Okay. They still require strongly typed languages because same thing, you have to be able to drop into a block of memory in order to chase the pointers. So you can't get away from strongly typed languages. You still need to know what is the type of each memory block. So essentially each memory block, instead of having 4 bytes, instead of having 4 bytes for reference counting, now each block starts with a pointer to a type description, like of a class or something. In Java, every class at runtime actually has an object that is a type descriptor for that class. And every object actually has a pointer to that class description. Okay. Now, the difference is you might say, why does a reference counter not need a pointer to the type descriptor? And the reason is reference counting is normally used with compiled languages. So they do the they insert the reference counting statements into the code and compile it. Mark and sweep collectors are being done dynamically at runtime, so they need the type information at runtime. Whereas with reference counting, the compiler extracts that type information and instruments the code directly with putting the reference counts before and after each pointer access. So with reference counting, you don't need a pointer to the type descriptor. It's done all in the compilation. But with mark and sweep, it's done at runtime, so you have to have a pointer to that type descriptor. Okay. And then finally, with mark and sweep, if you wait until memory is exhausted, well, what does depth first search require? It's recursion, right? What does recursion require? A stack, so that you can pop back to the previous element after you're done. So like here, when you're done searching here, you need to be able to pop back to here. And when you're done with this node, you need to be able to pop back to A. But memory's exhausted. So exactly where's this magical stack supposed to get its memory? Okay, it doesn't exist. So what happens in practice is they start reversing pointers. What they do is when you follow this next pointer to here, the garbage collector actually reverses the pointer so it can get back. And then when it gets back to here, it reverses the pointer again so that it restores it to its original state. But that makes, when you're no longer using a stack to do recursion, it's a lot more complicated. Hence, why the algorithms can be tricky to implement. So you say, okay, I will no longer, I don't want to reverse pointers. I want to have sufficient memory to do the depth first search. Well, now we're back to the incremental garbage collectors that require interleaving execution with and thread switching. So that again makes it tricky. So there's no way around it. These mark and sweep algorithms are tricky to implement. Okay. Then there's a variation called stop and copy. So what stop and copy does is it actually divides the space in half. So it says, okay, what we're going to do is we don't want to wait till it fills up. We're going to divide memory in half. When this memory gets full, we stop. We do the same mark and sweep stuff, but now anything that becomes useful, we copy down to here. And while we copy down to here, we compress memory, because before it was scattered all over. One of the other problems with mark and trace is you can get fragmented memory. And eventually you could end up not being able to allocate a big enough object. I need to add that to the disadvantages. So one disadvantage with mark and trace is fragmentation. And eventually memory can get so fragmented that you can't get a big enough space to allocate anymore. So stop and copy, what it does is actually compact memory at the same time it garbage collects by copying these things down. Now, when it does that, there's a little bit of an issue because anything that used to point, so let's say that you have a pointer from here to here. When you move this object A down to here, this pointer here in D needs to be updated so it points down to there. So you need to update your pointers with stop and copy. Okay, so here we go. Any pointer, so what you do is you leave a forwarding pointer. So as you stop and copy, what happens is when you move A, so when you move A, you leave a forward, let's say A goes to 0x20, you leave a forwarding pointer at A. So now when you reach D, you not only do you relocate D, but you say, oh, there was a forwarding pointer to A, so I'll also update the pointer at the same time. So every time you move a block, so when you move D, if D moves to 0x80, you would leave a so-called forwarding pointer at D to indicate that if you again encounter D on your depth first search, you have to update the pointer. I know I went through that somewhat quickly. Does that make sense what's going on? Okay. So this gets rid of memory fragmentation. It also eliminates steps 1 and 3 in mark and sweep because you no longer, with this technique, you just start immediately out here in the stack. Anything that you encounter gets moved down here. Anything that doesn't get encountered, well, you'll just free it up. When you're done with stop and copy, this entire piece of memory becomes free. So you don't need steps 1 and 3 anymore. You don't have to mark anything as unused. Anything that hasn't been moved out of here is unused. So it eliminates steps 1 and 3. And the disadvantage is very small because you say, well, you only now have half the heap. But in modern computers, you use virtual memory anyhow. So what you're actually doing is having virtual memory. And since half of infinity is infinity, I know I'm exaggerating, but half of a very large number is still a very large number. This isn't really an issue. Okay. I am out of time, so I will go over generational collectors next time, okay? And then just in case it's on the quiz, I don't think it is, but I'll just tell you the very simple thing with generational collectors is basically the most dynamically allocated objects have short lifetimes. So what you do is you put them in a nursery region. And only if they survive for some number of passes of the garbage collector do you move them to a more permanent region. So the idea is instead of having just one memory location, you have multiple memory locations with increasingly old objects that are more and more stable. So I'll talk about that on next Tuesday. And then next Tuesday, I think we also get into I/O, if I'm not mistaken. Yep. So Tuesday, we'll also start talking about I/O and Java. So you can create nice formatted input, nice formatted output, and you can reach from more than just the command line, which is what you're doing in homework 1. So have a good weekend, and I will see you all on Tuesday. For those of you who are